Every single day, automated systems categorize millions of documents, identifying spam and extracting customer sentiment from unstructured text. This text classification process relies on local pattern matching. To identify a negative review or a scam email, a model simply needs to locate specific linguistic groupings, like fast cash or boring plot, regardless of where those phrases appear in the sequence. For position-invariant feature extraction, convolutional neural networks are a high-performance tool. They already dominate computer vision by detecting localized patterns like edges and textures anywhere in an image. Applying them to natural language introduces a structural tension. Convolutions were engineered for fixed two-dimensional pixel grids, while language consists of one-dimensional, variable-length sequences. To bridge this gap, raw text strings are converted into a dense numerical tensor. The sentence length becomes the vertical dimension n, and the embedding vector becomes the horizontal dimension k. A standard two-dimensional kernel moving horizontally fails, splitting the vector to evaluate fractions of a word. The solution maps the convolution to one-dimensional movement. By collapsing the filter to match the exact width of k, the kernel is constrained to slide only vertically. As this one-dimensional filter slides down the matrix, it extracts local linguistic patterns by reading complete chunks of words at a time. By structurally compressing convolutions into a single temporal dimension, engineers can deploy spatial neural networks directly against natural language. In 2014, Yoon Kim formalized this logic, publishing the single-layer architecture that serves as a foundational blueprint for CNN text classification. Looking at the left side of this technical diagram, we see the n by k input matrix mapped alongside the parallel convolutional filters. The vertical axis represents the n component. This is the variable number of words contained within a given sentence. The horizontal axis represents the k component, defining the static or non-static word embedding channels. Following the dotted red lines reveals a strict architectural rule of this network. Every single convolutional filter must have a width exactly equal to the embedding dimension, k. Notice, however, the varying heights of these filters. The red kernel spans a different vertical distance than the yellow kernel. The height of the filter corresponds precisely to the n-gram size it is designed to extract. A filter covering exactly 2 rows detects linguistic bigrams. A filter covering 3 rows detects trigrams. As these filters slide down the matrix, they generate the resulting 1D feature maps shown in the center of the architecture. Because the sentence length n is inherently variable, the resulting feature maps generated by these convolutions are also of variable length. By running multiple filters of varying heights in parallel, the network simultaneously captures multi-word phrases, extracting localized semantic meaning regardless of where the words sequentially occur. These variable-length feature maps introduce a severe engineering bottleneck. The dense, fully connected layers that output the final classification require fixed-size input vectors, but language inputs vary. This standard diagram illustrates pooling, a downsampling method used to summarize feature presence and resolve dimensional mismatches. Specifically, max pooling isolates the single highest numerical value within its defined window, discarding the rest of the data. Returning to the architecture diagram, we see how the text CNN transitions from 2D vision pooling to 1 max over time pooling, applied directly to the 1D feature maps. 1 max over time pooling scans the entire length of a single feature map and records only the largest number it finds. Semantically, this maximum value isolates the strongest local linguistic signal, like the heavy polarization of the word boring, and separates it from the surrounding noise. Max over time pooling acts as a structural bridge. It decouples the architecture from arbitrary sentence lengths, compressing the data into a uniform output vector that the fully connected layers can process. While the single-layer architecture is mathematically elegant, deploying it in production requires precise hyperparameter tuning. To eliminate guesswork, researchers Ye Zhang and Byron Wallace conducted a sensitivity analysis, producing a guide for configuring these specific networks. Their first rule addresses the input layer. Engineers should initiate the model using pre-trained Word2Vec or glove embeddings, tuning them during the fitting process rather than starting from randomized states. For the pooling phase, their analysis confirms that 1 max pooling consistently outperforms average pooling for sentence classification tasks. When designing filter shapes, engineers must utilize grid search across different kernel sizes, typically ranging from 1 to 10, to locate the optimal n-gram lengths for their specific corpus. The overall network width, dictated by the number of feature maps generated per filter, is task-dependent and requires strict customized tuning. Finally, standard regularization techniques like dropout rates demonstrate minimal impact on the overall performance within this specific single-layer setup. The KIM architecture is not an unpredictable black box. It is a constrained system governed by proven empirical heuristics that guarantee a strong performance baseline. An alternative to this entire methodology is to bypass human-defined semantic word clusters entirely. This diagram details a character-level CNN, modeling documents using raw, single-character representations. The system begins with an input quantization process, converting characters into one-hot encoded vectors. Without pre-trained logic, the network deduces hierarchical structures, demanding depth with 6 convolutional and 3 fully connected layers. The primary advantage is morphological resilience. Working at the byte level solves out-of-vocabulary errors and allows the model to parse misspellings and emoticons without manual text preprocessing. The trade-off is data starvation. Because a character-level CNN must build the concept of language syntax from scratch, it demands significantly larger text corpora to achieve competitive accuracy. While morphological models offer flexibility against dirty data, they ultimately exchange the efficiency of semantic embeddings for architectural complexity. Whether tracking semantic words or raw characters, all CNNs suffer from a structural limitation. They possess no inherent memory of sequence order. Max pooling effectively extracts localized patterns, but by design, it discards the long-distance temporal relationships between those words. To solve complex grammatical tasks like subject-verb agreement or to execute deep language translation, a network must maintain a continuous, ongoing state. This requirement necessitates recurrent neural networks, architectures engineered specifically to process sequences token by token. Convolutions master the mathematics of spatial pattern matching, but true language comprehension requires a network architecture capable of remembering the past.